Now for stoichiometry part 3, where we deal with solution chemistry, specifically with molarity and the volume of a liquid. So let's have a little introduction. If I have the amount of a compound given as a liquid volume, not a gas volume like in part 2, and its molarity, that is its concentration, I can use this in stoichiometry problems. If we remember, molarity is often presented as capital M, but we should never use it as capital M. We should translate that to some number X moles of solute per 1 liter of solution. Here I'm giving you an example. If I have in my problem 5 molar HCl aqueous, that's my cat, I need to translate this into 5 moles HCl per 1 liter of solution. Now we will build a step-by-step process for solving these types of stoichiometry problems. As before, with stoichiometry, we have a chemical reaction. We cannot start with an unbalanced reaction, therefore we must balance it. In my example problem here, let me read it for you. Barium metal reacts with 167 milliliters of a 1.25 molar hydrochloric solution. What is the mass of the gas that is produced? Well, I've got a number of skills I must employ before I can even get to a chemical reaction. For example, I'm given the name of a compound. I must translate that into a formula, which I've done below. Also, I need to know what type of reaction this is and what type of products I will be producing. I happen to know that this is a single replacement reaction with an acid, so this is my special case number 1. So I have my reactants written out here, and I know I must produce hydrogen gas and then an ionic compound. I'll use my knowledge of ionic compounds, which I got from class notes 10, to know that my barium chloride must be BaCl2. Now that I have all my actors there in my reaction, I can now balance it. If I need to, I can go back to class note 17 to look at how to balance chemical reactions. And I have this reaction here at the bottom, which is now balanced. Now I can get on to solving my problem. We will be following the same sort of steps that we did in stoichiometry part 1 and 2. This is our step 2, where I find the units and label of my answer. Of course, that is, what am I looking for? So looking at the last part of my problem here, what is the mass of gas produced? Well, mass will give me my units. I can just say mass of gas, but it'd be much more useful in calculating to do grams instead of mass. And what is the gas? Well, we're only producing one gas, and that's hydrogen gas, which I get from my reaction. So grams H2 gas is the units and label of my answer. I'll be using this in step 5 when I do my calculations. Now for step 3, finding my compounds of interest. Because I'm using a chemical reaction, I need to link the 2 compounds that I'm interested in together by a mole ratio. We've done this before in our previous videos. So the first compound of interest is easy. It's the label of my answer. Remember, my answer units and label were grams H2 gas. So H2, hydrogen gas, is my first compound of interest. What about my second one? Well, I'm looking for a compound for which I know the amount. I have a liquid volume, and then I have a concentration. This will give me an amount of a compound. Which compound? Hydrochloric acid, HCl. So I need to link these 2 compounds together with a mole ratio, and for that I will need my balanced reaction. Here I'm going to use the coefficient of 2 for my HCl, and since there's nothing in front of hydrogen gas, I'm going to assume it to be 1. So I get the mole ratio of 1 mole of hydrogen gas is produced for every 2 moles of HCl consumed. This is a mole ratio, and it will be used as a unit factor in step 4. It's my first unit factor that I've calculated. Now for step 4, finding our unit factors. Most students find this very challenging and the most challenging part of the problem. So let's look at our first unit factor. We actually calculated this already, or found this in step 3, our relevant mole ratio, which we got from our balanced reaction. 1 mole of H2 to 2 moles HCl. We're going to use that as our first unit factor. Now we have an amount of a reactant. But remember, this is solution chemistry, and this amount of reactant actually comes in 2 unit factors. One is the liquid volume. That I have that in green. It's a plain number. 167 milliliters of solution over 1, because it's a plain number. The other part of that amount is actually given in our concentration. Remember, I said we're going to rewrite big or capital M as so 1.25 molar is going to become 1.25 moles HCl per 1 liter of solution. That's our second unit factor. Our fourth unit factor is actually given in our answer. We are coming up with the grams or mass of H2. So grams is a key word if you go back to class notes 13 for molar mass. Molar mass of what? Molar mass of H2 gas. And that is 2.016 grams hydrogen gas per 1 mole of hydrogen gas. Now, some of you may have noticed that we probably are going to need one more unit factor, which we will get off our cheat sheet. If, like we did in class, and you do that kind of mental calculation to take this from 167 milliliters to 0.167 liters, you won't need this cheat sheet factor. But if you leave it as milliliters, you know you're going to have to get from liters to milliliters, and 1 liter per 1,000 milliliters will come off our cheat sheet. In my calculation, I will go ahead and use this cheat sheet factor, but remember, if you do that mental calculation, you won't need this factor. Now I'm going to move on to step 5, where I'm going to compile my calculation. And now for our final step, assembling our calculation once we have all our unit factors. I've laid out all our unit factors on the bottom here so that we can kind of take a look at what we have to play with. The first thing I do is I put the units and label of my answer on the far right side, on the right side of the equal sign. My first step is I want to match my units and label of my answer with the best match of my unit factors I have down on the bottom. And I see my molar mass of hydrogen gas is the best match. Grams of hydrogen gas, grams hydrogen gas. So I'm going to put that, and I'm going to keep it the way it is because I want to start off my calculation string by matching those 2 units and labels. But it comes with a friend, of course, moles of H2 gas. Well, there's no moles of H2 gas over here, so I want to get rid of it. To do that, I'm going to have to find a unit factor that also has moles of H2 gas, but of course, it has to be on the opposite side. So if this is on the bottom, my unit factor next has to have moles of H2 on the top in order for them to cancel each other out. Well, that's my mole ratio. And I'm also going to keep it the way it is because moles of H2 is on the top. So now I can cancel moles of H2 on the bottom, moles of H2 on the top. But of course, it comes along with a friend as well, moles of HCl, which is on the bottom. I need to get rid of that. So I need to find another unit factor that has moles of HCl, this time on the top. Well, my concentration is a good candidate right here, moles of HCl. And fortunately, it happens to also still be on the top, so I'm going to keep it the way it is. So my moles of HCl on the bottom here will cancel out with my moles HCl on the top here. Now I'm left with liters of solution. So you have 2 courses of action. We're going to assume that I'm going to stay with 167 milliliters and not do my mental calculation. If you do your mental calculation and translate that into liters, the 0.167 liters of solution, you won't need this unit factor. This is the unit factor from my cheat sheet. 1 liter of solution to 1,000 milliliters of solution. And again, I like it the way it is because my 1 liter of solution will cancel out with liter of solution. Now I'm left with milliliters of solution on the bottom. My plain number takes care of that. I have milliliters of solution canceling with milliliters of solution. If I go ahead and do my calculations and round appropriately. Let's see, let's look at our significant figures. 3, this is exact. This is 3, and this is exact, and then 4. So I'm going to have to round to 3 significant figures, and what I end up with is 0.210 grams of hydrogen gas. So now my calculation is complete and rounded appropriately.